Hi, Mr. Bonney, back with another botany lesson, this time a continuation of photosynthesis. We're going to take a look at the Calvin cycle. Now, as we take a look at this, first and foremost, we realize that it is exactly that. It's a cycle. There's no official start and end point to it, because the things that are going to be used will be regenerated at the end. If you want to look at a start point, you could look at it as starting right up here, where we have the input of carbon dioxide and then an output down here of G3P, which is eventually turned into glucose. But what's important is that all of the things that are used get regenerated, and this can happen over and over and over again, because it is exactly that. It is a cycle. We're going to start at first by looking at this first phase, which is what we call carbon fixation. And carbon fixation, essentially what it is it's taking an inorganic form of carbon and that of carbon dioxide and turning it into an organic form of carbon. So just some review there. Inorganic means, in this case, it's not something that you would find in living things, or it's not usable by living things. And organic would be. So organic compounds that you're familiar with are carbohydrates, lipids, proteins, nucleic acids. And so this process right here can't be overlooked, because we're taking things that are not found in living things, in this carbon dioxide, and converting it over into something that is. Here's a bit of the text from what I was just speaking about, so feel free to pause on this text to fill in your notes. But ultimately here, the main takeaways is that this is a cycle, and that carbon fixation converts inorganic carbon over into organic carbon. This process of the Calvin cycle is taking place in the stroma. Now remember, the light-dependent reaction happened on these thylakoids, specifically on the membranes of the thylakoids, some of it in the lumen, and then some of it just was made in the stroma. If you remember, at the end of the light-dependent reactions, both ATP and NADPH were made, and they were made in the stroma. So they're already out here ready to be used. Remember, the stroma is this grayish colored space, or the filling space outside of all of the thylakoids. So let's take a look again at these first steps of the Calvin cycle. As I mentioned, carbon dioxide is going to be brought in, and it's going to be combined with a chemical compound called RUBP. There's an enzyme. The enzyme is called Rubisco, and what it does is it catalyzes this reaction between RUBP and the carbon dioxide to make another chemical compound. And this chemical compound is called 3-PGA. And what's important here is to note that it is an organic compound. So the combination of this right here, RUBP, which was left over from before, we'll get to that when it cycles back, in combination with carbon dioxide, is our first phase, which we call carbon fixation. Again, the idea here is we're taking inorganic carbon, combining it together to make an organic form of a carbon compound right here in 3-PGA. Now, if we take a look at the amount of carbon that's present, if you look at RUBP, it has 1, 2, 3, 4, 5 carbons, and each carbon dioxide has 1 carbon. We look at the total amount that's made then, if you look at the 3-PGA, it has 1, 2, 3 carbons. So because there are only 3 carbons in here, there needs to be more of them made. And that's what this number right here refers to, that there's 6 of these made. We started with 3 RUBP. 3 RUBP times 1, 2, 3, 4, 5. That means there was 15 carbons here to start with. There were 3 carbons here to start with. So 15 plus 3 means that there should be 18 carbons total. 6 times 1, 2, 3 means 18. The total number of carbon is conserved, is what I mean by that. It's kept the same when just through these chemical reactions. We're combining together this with this, and we get these 3-PGA. Here is all of the text from what I just said. Next phase for the carbon or the Calvin cycle is to then take that 3-PGA and we're going to convert it into something else. Now there's 2 phases that it's really a really good way to describe this would be rearrangement. Reduction is just simply because there's reducing agents are being used. They're chemistry, oxidation, reduction reactions. But rearrangement would be another good way to describe this. We're going to basically take this 3-PGA and we're going to use energy from both ATP and NADPH to convert it over into something else, the end goal being G3P. So the first step is to take the 3-PGA, and then energy from ATP is used to turn this into 1,3-BPG. Now this ATP right here came from the light-dependent reaction. This is one of the first things that the transfers over where we see the light-dependent reaction is needed. The second then is we convert this 1,3-BPG into G3P. Again, energy from NADPH is used to do that. Also, NADPH came from the light-dependent reaction. Now, both 1,3-BPG and G3P are three carbon sugars. So the amount of carbon stays the same because look at there's 6 of them here and there's 6 of them here. So the amount of carbon hasn't changed. They're just different chemically. They've been essentially rearranged is the way that I would describe it. Some of their chemical bonds have been broken and new ones have been made. What's important to note then too is that this G3P right here, one of them is going to be removed. This G3P then is essentially the product of the Calvin cycle. This is what get removed. Now notice how it is not glucose. We always talk about glucose being the end product. We'll get to that in a minute. Again, we had a one rearrangement here from 3-PGA into 1,3-BPG using ATP, and then another rearrangement from 1,3-BPG into G3P using energy from NADPH. Both of these came from the light-dependent reactions. Here's all of the text from what I just mentioned. Just a couple additional things here. These are the names of the enzymes that cause those reactions to take place. Just threw them in here as well. Right, as I mentioned before, G3P really could be considered the final product of the Calvin cycle, but most often what happens is that G3P is converted into glucose. The way that happens is we take 2 G3Ps and combine them together. Remember that G3P was a 3-carbon sugar, so what happens is that it's combined together with another one. Now you have the 6-carbon for the C6H12O6 of glucose. So really it takes 2 full turns of the Calvin cycle to make 1 glucose. Now there were 6 G3Ps made. The other 5 are going to be used in a regeneration process that's going to regenerate that RUBP. So let's take a look at that. So our last step then here of the Calvin cycle is to take, remember here was our 6 G3P that were made. 1 of them was removed. The other 5 then are going to be transferred back into RUBP by using some final energy from ATP. And again, take a look at the number of carbons here. There's 1, 2, 3 carbons inside of G3P, and there's 5 of them. 5 times 3 is 15. Look at RUBP. RUBP has 1, 2, 3, 4, 5 carbons inside of it, and then there's 3 of them. So 3 times 5 is 15. So the amount of carbon stays the same each time. So this additional input of 3 carbon dioxides right here that we started with eventually comes out right here as the output of G3P with its 3 carbons. Again, taking note that we just make 1 G3P as an output. In order to make glucose, we need 2 of these, so this whole process then has to happen again. But now we can see the idea of how this is actually a cycle because the RUBP was regenerated so that it can be reused again with an input of more carbon dioxide from the environment. This, again, here's all of the text of what I just said, and with a finality here of noticing that now the Calvin cycle is done. Okay, so again, the G3P from it can be turned into many types of carbohydrates. Glucose and fructose tend to be the most often ones, with glucose being by far the most frequent one. Any excess glucose then can be used to be stored as starches or even be converted over into cellulose to be a building material. This is, again, the main goal of what plants are looking to get out of photosynthesis is this glucose here. Again, so just a brief recap of the whole process of the Calvin cycle. We have carbon dioxide brought into the environment of the leaves, into the stroma of the chloroplast, and those come in through those stomata. Then we start with the process of carbon fixation, converting inorganic carbon dioxide into an organic compound. Then there's a couple rearrangements. This is where ATP and NADPH are used. And that we got the NADPH and ATP from the light-dependent reaction in order to make G3P. Some of that G3P is taken away to make glucose. The rest of the G3P is used to regenerate RUBP. And now we have a final outlook of the whole process of photosynthesis. Over here on the left-hand side, again, we have the light-dependent reaction. Water was brought in. It was split with light energy was used. We made oxygen gas. ATP, NADPH were our products of the light-dependent reaction. They are used over here in the Calvin cycle. In the Calvin cycle, carbon dioxide is brought in. Carbon fixation happens between RUBP. We make 3-PGA, there's its longer name. Then ATP and NADPH are used right here to make some G3P. One of the G3P is removed to make sucrose or glucose, just a sugar. And then the rest of the G3P is used to regenerate RUBP again. And this process can happen over again. ADP is the less energetic version of ATP. NADP plus is the less energetic version of NADPH. Those make their way back over to the light-dependent reaction where they can be used again or recharged again so that they're ready to use again and again and again. This final page here kind of shows where things go when we talk about the reactants and products of photosynthesis. So here up top, you have the reaction of photosynthesis, carbon dioxide and water to make glucose and oxygen, noting that the carbon dioxide, the carbon in the carbon dioxide goes to the glucose. The oxygen in the carbon dioxide goes also to the glucose. Notice the water that we're using, the water, all of the oxygen from the water is the byproduct that gets, the oxygen gas that gets put out into the atmosphere. And the hydrogen from the water is where the hydrogen goes to make the hydrogen inside of glucose. And so there we have the whole overall look at the process of photosynthesis, quite an in-depth one. And again, looking at our chemical reaction here, carbon dioxide plus water to make glucose and oxygen. And again, glucose being the primary end goal, the primary product of photosynthesis.